morning, everybody. This is certainly a much larger room than the very first one that we held in NASA Ames. Anyway, a lot of you know me as from the Quantum Computing Report, but I do want to let you know that consolidation is happening in the industry, and I'm actually a case study. I am getting together with a gentleman in London, David Shaw, who runs Fact-Based Insight, as well as Andre Koenig, who runs Interference Advisor, and we are creating a business intelligence company. Quantum is just getting so big that we need more. The three of us can no longer do it on my own, and we'll be providing services and data to help people in the industry grow and advance, give them intelligence that they need to plan their efforts. So with that, let me talk to you about sort of some of the taxonomy of how we're looking at the whole market. I know most of the presentations today, I think, are on quantum computing, but quantum communications and quantum sensing is very important, and they feed into each other, too. There's a lot of technology that you may develop for quantum sensing that you'll use in a quantum computer or in quantum networking, too, because we feel that networking will be very important for quantum data centers in the future. So I won't go through this slide entirely. I know it's a big eye chart, but hopefully QCware will post this, and you can look at it in more detail when you have some time. But the way to read this chart is on the left. I guess this left would be this way for you. It starts with the components, and it goes through the hardware, and then the software, and the applications, and then the end markets are on the right. And you can see how everything feeds together. It's a very complex market. We are tracking over 600 companies that participate in the quantum market. So who's doing what is going to be a big challenge. But I will focus a little bit on the hardware, quantum computing side for a bit, and point out that at the end of the day, to provide service to an end user who wants to get a real-world solution, you need to create a full quantum stack, starting from the chip at the very bottom, all the way through the control electronics, the control software, the frameworks, the integrations, the applications, and one thing that we've added, which no one else has, but I think is very important, is a user community. You need to have a full stack of people, because quantum is complex, and at the very top, you're going to have end users who want to use this stuff, and they're going to have to they'll work with the user community to look at open source software, to get education, but you're going to have to do all of these things to provide value to an end user. So for companies that are in this space, it is very, very important to partner. Not even the biggest companies can't do all this on their own. So partnerships are key, and that's why meetings such as this are so important. And again, I won't go through, again, all the individual elements that are in this chain, but what I want to do is talk about the ones that are most difficult. I will remind everyone that quantum technology is hard. It's one of the hardest technologies we have. And you see on this slide here some of the challenges that the quantum providers are going to have to face in order to solve problems. You know, you're going to need millions of qubits, and I'll show you a slide on how many millions in just a few minutes. Error rates are critical. I heard earlier today a very important point that today's error rates, even in the best of computers, are really not good enough to solve real-world problems, to do error correction that's meaningful. Networking is also going to be important. For those of you who were here last year, I made one prediction that quantum data centers are going to be very important, particularly at the early stages, where you're going to have multiple quantum processors, and they're all going to be connected by fiber optic cable and exchanging entangled qubits with each other to get to these millions of qubits that you're going to need to solve real-world problems. And this is an example where technology being developed in quantum communications is definitely going to be directly applicable. The good news about a quantum network is that you don't have to worry about the long distance problem. In quantum communications, of course, fiber optic cable has losses, and you need things like quantum repeaters, which are still in development. But if everything's in one data center, you're only traveling a few meters, that's not a problem. Error correction, there's been a lot of very good papers this year on error correction. We see advancements, but I think more work is going to be done. One of the trends that we see at GQI is that people are looking beyond the surface code. Surface code has been widely used, but people are now looking at things like LDPC, low density parity check, which is a more advanced code. Gate speeds are important. Here's a metric for you. In a modern semiconductor process, the gate of a semiconductor is about 0.1 nanoseconds. You compare that with something like a superconducting processor, which may be 100 or a couple hundred nanoseconds, or ion traps or others where the gate speeds are in milliseconds. So classical computing has a fundamental speed advantage if you look at it on a gate-by-gate basis. The reason quantum computing will win, though, is the algorithms are more efficient. You'll have exponential scaling versus classical. I talked about full stack. Software is critical. Making it easier to program, I think there's a big problem. We talked about workforce development, but being able to tie the end user, the subject matter expert, someone like the logistics analysts or the chemist, and have them profitably use a quantum computer requires a lot of good software and making software easy to use. Again, we see a lot of progress in that area. Reliability is key. There will be some companies that will want to call quantum computers on an hourly basis, even daily or even minute by minute. And 24/7 availability is important. Not all the companies out there can do that right now. They have limited hours. They got calibrations to worry about, maintenance, and that's a big issue. The other thing I would point out is the classical community is not resting on its laurels. Every day, every month, we see new papers about some new classical algorithm that is doing what people thought you could only do with quantum. And that is, it's a constantly raising bar. When you talk about quantum advantage, it's a constantly raising bar. You're going to have to continue to improve. And one thing that's pointed out in previous meetings, I'll repeat, there's something called quadratic scaling. And Grover's algorithm, for example, is quadratic scaling. And the belief right now for many quantum experts is quadratic scaling will not be enough to beat classical. You're going to need exponential scaling or something like that in order to do that. But beyond this, there's something else that I am actually quite concerned about, which is pricing. And no one talks about it at this point, and the reason they don't talk about it is due to the fact that they got to get the thing to work first. But pricing is also going to be important. Not only will the providers need to make it workable, make quantum computing feasible, they have to make it economical too. And I'll show that in the next slide. So one of the things we're looking at is a new metric, which I call qubit seconds. Because a provider, of course, if they had a 100-qubit machine and a 1,000-qubit machine, they're not going to be priced the same way. So you may have other metrics to use, but we'll do this. But right now, the pricing is way, way too high. And if this problem is not solved, then the quantum industry will never be a billion-dollar market, a multi-billion-dollar market. It'll be maybe a multi-million-dollar market, but for those big applications where there's lots of money, lots of potential, lots of revenue, you're needing to solve the pricing problem. And just to show you an example, this is a spreadsheet experiment that we did. There is a very good paper from Microsoft that was just posted a couple weeks ago on Archive on resource estimation. And what Microsoft did is they took 4 different applications and they made 6 assumptions for different processor configurations. The assumptions were based on the gate delay and the error rates. I will say the bottom 2 of those 6 in each category is Majoranas, as you might expect from Microsoft. And if you look at the white columns on the sheet, and it may be hard for you to read the specific numbers, but you can see it in the Microsoft paper. We took this directly out of the Microsoft paper. You can see the assumptions that Microsoft made. And then we did a rough assumption with regards to what is pricing today with regard to qubit seconds. And we came to the conclusion that roughly, maybe an order of magnitude plus or minus, pricing of computer time is about 1 penny per qubit second. So at today's pricing, if people were able to produce those machines, you're going to start seeing job run times in the billions and trillions of dollars. And it's just uneconomical. A lot of work is going to be needed to get the pricing down. And I know it's early, but it's going to be very, very important, particularly once the machines get more practical. And that's not impossible. The semiconductor industry has, of course, been doing this for a long time. Over the past 40 years, the cost per transistor has gone down by 10 orders of magnitude. So there's a lot of work involved, scaling up, economies of scale. Switching technologies might be one of the things that people will have to do. The graph on the right shows you what happened when technologies switched in semiconductors. The early semiconductors, from Bell Labs, were what's called bipolar technology, and that was king of the hill until about 1980. And after 1980, MOS transistors came along, and they were smaller, they were faster, they were maybe not faster, but cheaper, easier to, and more scalable. And at the end of the day, in 1980, there was a crossover. So not only was there a crossover with regard to the technology, but crossover with regard to who the leaders were. The leaders in bipolar were companies like Fairchild and TI. Motorola was the leader. After that, it was companies like Intel, TSMC, Samsung, many of the others. So there could be a crossover in terms of technologies in quantum that we may see, but still the technologies we have today may still have a 20 or 30 year lifetime to be viable. So one of the things that makes me optimistic is the fact that there are a lot of different people working on different technologies. We're tracking like 10 different technologies, efforts, modalities to build a qubit. We have a total, we're tracking a total of 160 different projects by 125 organizations. And even though I believe that many of those will fail, some of them will work out. And some of them will be very, very cost effective. And I think that's why the industry will be able to solve some of these pricing problems that I was just talking about. So what this means is that the industry is going to be very dynamic. Going back to the semiconductor industry, the reason we're called Silicon Valley was we had so many semiconductor companies in the 1960s and 1970s that were here. And a lot of them over the years have merged. There's only a handful of pure semiconductor companies left here in Silicon Valley. And I don't know how many fab facilities, probably only a handful of fab facilities. So I think a similar thing is going to happen in quantum. And we're already seeing evidence of that. This is a listing of consolidations that have happened so far. So I think there are going to be more. It's going to be a very dynamic market. There'll be some companies that go out of business, and leadership will change over the years, but that's inherent in every technology. So Of course, as I said earlier, my company is sort of the latest example of that. So we will see that. But sort of to reiterate, some of the points that were made is that quantum does indeed have a wide industry impact. This is a chart we've created, shows the worldwide global economy, which is about $95 trillion. And my data says that the semiconductor and computer industry is about 10% of that. On the right, where it says use cases, are all the various use cases that we see in quantum. And then you can see we've broken down the economy into various sectors, the primary, industrial, services, and then subdivided that. And what this chart shows is which use cases are applicable in which industry sectors. So again, it's going to be a very widespread. There's a lot of opportunities, but we're going to have to solve those problems that I talked about in order to really take advantage of those opportunities. So to close, I'm going to leave you with something called Amara's Law, which is that people tend to overestimate the potential of a new technology in the short term, but they underestimate its potential over the long term. And the example I would give is when John von Neumann invented some of the first computers in the 1940s, I don't think he anticipated Facebook or GPS or some of the newer AI programs. So there are going to be things that people will do with quantum that we never, ever anticipated, and it's going to be an exciting journey. So with that, I want to thank you. Again, our new website for Global GQI is there, global-qi.com. The Quantum Computing Report will still be around. It'll be a brand underneath Global QI. We will still have our weekly newsletter. We publish it every Sunday about the latest happenings, and it's free, so I'd encourage you to sign up. So with that, that's all I had. I think we have a couple minutes for questions. So does anyone have any questions? Any questions? Yes, there's a hand there.
Could you speak a little bit to the evolution of the community in the sense of how you might have seen a Red Hat develop and building its developer community and the outreach to the non-Linux kernel builders? Are you seeing that happening in the quantum computing space where more community is coming that's not just working on the primary physics challenges?
I don't think it's happening in any organized way, but I think many different companies are putting together stuff. One of the things that's encouraging is the quantum hardware companies. Several of them are offering education classes. They're sponsoring hackathons. A lot of is happening in the open source community. There are certain efforts in order to make more of the software available in open sources. And you'll continue seeing it, but I think it's going to be an ad hoc way. I don't think you'll see any government agency, for example, trying to organize it. Maybe the closest we have are things like the QEDC or the QIC that are putting together consortiums of people that work on various topics to help advance the industry. Okay, anything else? Okay, there's one right there in the front.
Thank you, Doug. That was great. I have a question on quantum sensing. You alluded to that. Where we were there, I heard that British Telecom did a trial using quantum sensing, antennas and all that. How do you see that ecosystem evolving?
Yes, that's a very, very good point. I only got 20 minutes from Yanni for this thing, so I had to focus a little bit. But quantum communications is very important. There's a lot of activity there, and you can see me offline. I'll tell you more about that. Quantum sensing is very interesting. Quantum sensing may be the thing that we see some of the advantages come in first. One of the advantages of quantum sensing is you don't have to worry about end-user software. Maybe you need firmware inside of the sensor, but you don't need these complicated complicated end user types of things. You probably won't need a lot of hybrid classical quantum integration to that. So quantum sensing will have a big impact in things like medical approaches, navigation. One thing I heard is that Boeing is going to be we'll have an experiment, I think it's next year, to navigate a plane without GPS using quantum sensors. So that, as well as things like magnetic sensors for exploration, because the magnetic field of the Earth changes, and you may be able to run an airplane with a very sensitive quantum sensor to be able to figure out where the deposits are. Okay, with that, I think I've run out of time. Again, thank you very much, and I'll be around for the next 3 days if you have any more questions for me. Thank you.